So today we are missing co-op because of the snow that's outside, and so I know that you wanted to learn about Module 7, which is uniform circular motion, so I'm going to try and cover my lecture here today on my whiteboard. Hopefully answer any questions you have. So we're talking about uniform circular motion, and that means that an object is in motion in a circle with a constant uniform speed. So we know that the formula for average speed is distance over time. And in a circle, we know that the distance that it's going to travel is going to be the circumference of the circle. And so that will also be over time. Usually when we're talking about circular motion, time can also be written as a capital T, which stands for the period of the motion. And we'll talk a little bit more about period and frequency in a second. So when something is moving in a uniform circular motion, its path can be traced as a circle. So we know that it has an acceleration because we know that although it's not changing speed, it is changing velocity. We know that if something were not acting on the object, it would continue in a straight path perpendicular to the motion. So the velocity vector is actually perpendicular to our circular motion. So at any point on the circle, if it was not moving inward, the object would travel in a straight line perpendicular to the circular motion according to Newton's first law. So the direction of the velocity can also be described as tangential. So it travels in a tangent. So how about the acceleration? Hopefully from the lab last week you were able to determine that acceleration in circular motion is always projected inward. And so this is where we get the term centripetal acceleration. So centripetal actually means center seeking, and it's not to be confused with centrifugal, which we all know we shouldn't use the F word. So do not use the word centrifugal, because that means outward, and so that's not what we're talking about when we talk about centripetal acceleration and centripetal motion. I had a good thing for you to see. Hopefully you were able to determine last week in your lab that the acceleration was inward. If Leah comes up here, we'll do a little demonstration where you can actually see an object accelerating inward. Okay, so if we have an object moving in a circle, it's experiencing an acceleration. We already said that the acceleration is going inward due to the change in velocity, because something is always causing the object to go in a circular motion as opposed to a straight line that it would naturally want to go into, and that's known as the centripetal force requirement. And so objects in motion tend to stay in motion with the same speed in the same direction unless acted on by an unbalanced force. That's, remember, Newton's first law. And so in a centripetal motion, we know that there is unbalanced forces because it's not moving in a straight line. So any object moving in a circle experiences a centripetal force. And so as we write our force notations, we're going to write it as the force centripetal. And we're going to be able to determine how to figure out the actual Newton's worth of force that it is feeling. So anytime that something is changing, it's experiencing this centripetal force. So if you're in a car and you're making a turn, the friction on the road is going to help grip the tires and cause that centripetal force will be equal to the centripetal friction. Otherwise, you'll go sliding along if they're not equal. By the same way, if you put a bucket of water on a string and you're spun it around above your head, the water would not come out due to the force of the centripetal motion. And it's the same thing that keeps the moon orbiting around the Earth and the Earth orbiting around the sun. Okay, so now, of course, you want to know the mathematics involved in centripetal motion. And so we said that the average speed is distance over time. We said that the distance in circular motion is the circumference. And I'm going to assume that you know that the circumference is also to equal to pi r. Just to review really quickly, when you have circular motion, the radius is from the point of a circle to the outside of a circle. So any time you have any type of circle, r stands for radius. And the circumference means if you had something that was traveling around the circle, it would travel a distance of 2 pi r to get around the circle, the circumference. So we can use knowing this about the circumference in order to solve for things with centripetal acceleration and motion as forces. So we can then say that the average speed of an object could be 2 pi r over time, substituting in for that other equation that we had, distance over time. And so the centripetal acceleration can be the velocity squared over the radius, and if we substituted in our old formula into there, it could also be 4 times r 4 times r times pi squared over time squared. We got this one by substituting in that formula of the 2 pi r into here, and we get that formula where v is velocity, r is the radius, and the t is the time that it takes to go. So we talked a little bit about period. T stands for the period of the motion, and period is how long does it take for the thing to make one whole revolution. So time of revolutions. The other thing that can be helpful when we're talking about circular motion is the frequency. So those of you that took chemistry, hopefully you remember a little bit about light. We'll get more into this when we get to our light unit in physics. But frequency is the relationship of 1 over the period, and it is the number of trips it makes per second. So if this were to go really, really fast in 5 revolutions every second, that would be its frequency. And so frequency is measured in 1 over seconds, and hopefully you remember that this is also known as Hertz, for Rudolf Heinz Hertz, who discovered that. Okay. So hopefully this is all making sense, that you did the reading and it's making sense to you. I wanted to do one of the on your own, just to be sure that we're getting this all okay. So I'm going to work on your own 7.3, and if I had the book I could tell you what that said. Okay, so it says a child twirls a 314 gram, I'm going to switch it to kilograms right away, toy around his head, and he's got a 67 centimeters, so I'm going to change it to meters, string that the plane's attached to, and it can withstand a tension of 18.1 newtons. So that's the force of tension. This is the radius, and this is going to be the mass. And so we are using the formula that centrifugal force is equal to the mass times the velocity squared divided by the radius. So this is a pretty straightforward plug and chug. And so we know that we can rearrange, we can plug in here for the force we're trying to solve for the maximum speed. So we're going to rearrange this formula to solve for the velocity. So we do that by this. Since we have circular motion, we know that the tension on the string is going to be equal to the centripetal force. So we can say the centripetal force times the radius divided by the mass is going to equal the velocity squared. So we're going to have to take the square root of that. So hopefully you were following as I rearrange that. I multiply by the r, leaving me with that, divide by the mass, giving me velocity squared, taking the square root of each. So if I plug those in, I get 18.1 newtons times 0.67 meters. Make sure that all your units agree. Times 0.314 kilograms. And I want to take the square root of all of that. And that will get me 6.2 meters per second. That's the velocity that the child can swing the plane before the string breaks. So hopefully that makes sense to you.